everyone. My name is Naini. Thanks for the introduction, sir. So as sir mentioned, I work as an education technical evangelist. I'm based out in Bangalore so far, and along with me is Ramana and Anand. We all three of us work for the education technical evangelist team. Myself and Anand are based out in Bangalore, and Ramana is based out in Hyderabad. So what we do mostly as tech evangelists is to engage with the research scholars and the professors and the students as well to on the adoption of MATLAB and Simulink in curriculum as well as research. So today's topic, which is around electric vehicles, so what we are going to present on is model-based design for electrification of vehicles. I'm sharing the screen. Okay, so this is what our the topic for discussion for today is model-based design for electrification of vehicles, and also we'll have one demonstration on basically how we can design and implement the digital controllers for power converters, which again is a very key component for the vehicle electrification, right? So I'll get started. In between, if there are any questions, please feel free to write the questions in the chat. Ramana and Anand are there along with me in the call. So we'll address those questions in the end or probably in the middle as well. For now, I would request you all to please mute yourself and we'll start with the presentation. So we'll start by talking firstly about the technologies which are basically contributing to reduced energy emission and consumption, be it your e-mobility or your charging stations, which are again a very important component for the electrification concept as a whole. If we talk about the renewable energy systems and specifically if we talk about the internal automotive electronics as well, which one of the components of that maybe the headlamp, where we are talking about conversion of electrical energy from one form to another. So if we talk about all these things, that's where electrification or the components of electrification, be it the power converters, battery modeling, or the motor control systems. So all these things become the key components, right? Starting with an overview or the system of electric vehicle, I would request you all
Participants,
to
please
mute
mute.
yourself. I think somebody is
I'm sorry, ma'am.
not on mute.
Ma'am, sorry, ma'am. Sorry, ma'am. 1 minute. Ma'am, sorry, ma'am. 1 minute, ma'am. Ma'am, sorry, ma'am. You can continue now, ma'am.
No problem, sir.
Okay.
So if we talk about electric vehicles, so that is also, which is again one of the very upcoming technologies and also which is the main topic for discussion for today. So if we talk about the entire EV as a system, we start with something as a grid. That's where the source of our power is, and that power is being fed into our output, which is basically in this case the load, which is our electric vehicle. And in between, the different key components which are involved in this system is the charging stations. And then charging stations has a form of energy which cannot be taken directly into our electric vehicle, so they are converted from one form to another using the converters. So what we see in electric vehicle as a system is we start with the battery charger, which is converting the AC form of voltage to a DC form of voltage and is being fed into the battery pack, which is our storage for the energy. And then this particular energy is converted to another form, which is the AC for driving the electric motors. So what we see is it has different components starting from the grid, the charging stations, the power converters, the AC to DC converter, the battery pack, again the DC to AC converter, basically the inverter. So electric motors are there. And if we also see there are DC to DC converters as well. For example, if we talk of the headlamps of the car, that's where the higher DC voltage is converted to a lower DC voltage. right? So this is not just it. It's what we talked about is mostly the electrical component, but in the EVs, there's another key component which has been shown here in this dashed green box, which is are the which are the vehicle dynamics, which is not the electrical part, but also has the dynamics or the mechanical components of the electric vehicle involved with it, right? So whenever we're talking about a system, in this case, which is an electric vehicle, we talk of all the domains together, be it electrical, mechanical, or if the controls which are involved in, controlling the entire plant, in this case, which is an electric vehicle, right? And if we see in this case, which is our electrical part, the key components which are there are motor modeling, which is again, it's important for the electric vehicle, battery pack, uh, the battery management system needed, and the converters, right? So what we'll do is we'll give you an overview of how MathWorks solutions are there for modeling and simulation of electric vehicle for all these domains. The approach will remain the same, and we'll do a deep dive demonstration of the power converters. So just to give an overview, we have the existing models available for motor modeling and control. There are different inbuilt examples, ready-to-ship examples, which are there for DC motor, PMSM model, BLDC motors, which are there. So all these models are a part of the examples which are already there. So what you can do is make use of these existing examples and use them as reference or as a starting point, and then start to build on top of it. I'll show you how you can do a demonstration. And if you're talking about such a process, why we call it as a model-based design is because the next we are moving to discuss on a future design, but it's important to understand what is the traditional design process. So whenever the engineers they had to design a certain application, it always starts with the requirements. For example, if a manufacturer has given a project to the supplier, they will always start by giving the textual requirements to the supplier, and these are then segregated by the engineers who are from different domains, be it the controls, mechanical, or the electrical engineer. And they used to segregate the requirements, and accordingly they used to make their design, right? So the design earlier which was being made was irrespective of the other domain. So once the control design once the design is complete, then the engineers used to spend extra amount of time on doing the implementation part, which means the code generation, right? So what they used to do was to spend a lot of time on designing the process, designing the requirements, making a concept out of it, and then after the design was done, they would spend another span of time on doing the handwritten coding, which used to take more time for implementation. And then definitely when they're integrating their controls with other domains, that's where the errors used to come up. So where are these challenges coming from? One is the requirements may change. The manufacturer may ask for a different requirement every time, right? Or if you're spending so much of time on the designing part, then you're spending another span of time on handwriting the code. That's where the process becomes slow. And when another thing is the key thing is the integration part. When you are integrating the controls, mechanical, and the electrical domains together, once the designing was done, that's where the errors come up, because all these designs were not done at a single platform. If you're doing it on different platforms and then you're trying to integrate to understand the systems perspective, that's where the errors used to come up. Again, because the errors are found late in the process, that's where the expensive prototypes comes into picture. You have already built in your prototypes, and if your process is not correct, if there are errors because you have found them later in the stage, it actually leads to the loss of money as well, because you have spent so much on the expensive prototypes. So to address this, the engineers, so this is specifically from the automotive background, but this also applies equally to the aerospace industry as well. So what happens in model-based design is the entire thing, which was the segregation of requirements in different domains, now gets into a system level design. Now the engineers will be talking on terms of system, and then they will divide it into the key components for that. So there would be models for controls separately for mechanical and for electrical as well, but it will always be seen as a systems perspective, a design, the systems perspective, the design should have a systems perspective with it, right? And what also model-based design workflow offers is, when you have a control design, if you have spent a lot of time on designing that particular process, modeling that, then why to spend extra time to handwrite the code? So what happens with the model-based design workflow is automatically the code is generated. So it gives us the capability to automatically generate the C++ code from the models and deploy it to the hardware, right? And it goes not just for the controls, but also for the plant model. If you are making your plant model as well, you can also generate the code, put that into the HIL systems, that is the hardware loop systems, and then do the system level implementation, right? So you do the C++ code generation for controls and the HTL code generation if needed for your plant model. One very important thing which comes with model-based design is this particular bar on the left-hand side, which is the testing and verification. So the capabilities of model-based design also comes into picture when you talk about the verification component. So the testing and verification is done at each and every step, be it the level between the requirements and the design, and then the design to implementation, right? So the testing is done. For example, if somebody is working on a safety critical application, if they're working on a pilotless flight, or if they're working on an autonomous system, the process won't be completed unless if it is compliant to certain standards of the industry. That's one thing. And it's not complete if the particular testing, rigorous testing and verification is not done. So in that case, the testing and verification plays a very important role in the model-based design workflow. And that's how this process is also applied to an electric vehicle. We'll see going forward how it is applied. So far, is there any question?
In the chat window, there are no questions, but the audience can ask.
Yeah, please feel free to write the questions in the chat if there are any.
Ma'am, you can proceed, ma'am.
Okay, sure. Anand, I wanted to check
Okay.
the voice and the screen, the slides are clear, right? There's no lag?
Yeah, it is okay. In between, the voice was breaking for a while, but again, now it is clear.
Okay. Thank you. So I'll proceed further. We'll see how the model-based design workflow works with Simulink. So for the ones who are new, MATLAB and Simulink, MATLAB is a base tool by MathWorks. Simulink is another tool on top of it. And unlike MATLAB, Simulink is basically a graphical interface. It is a dynamic simulation environment where you can model and simulate your dynamic systems, right? So whatever is built in Simulink is basically a model which is built, which is designed with simulation. You also mentioned the executable specifications for your model while you are building the model, and the continuous testing and verification is done. So that means whenever you're designing along with the simulation. So it's basically a simulation-based designing, right? And then it also gives you the capabilities for auto code generation, which takes away your effort to manually write the code, right? So that's what the entire model-based design workflow with Simulink looks like. If we talk of motor as a system, which is here in this case, if we talk about a closed loop model, where we have a DC motor and we have a controller as well, will simulate the closed loop behavior of this particular system in a simulation environment on a single platform. And once the simulation works fine, will automatically generate the code for the controller and then deploy that code to the hardware, right? So that is where our processor and loop simulation can be done. So, if we talk about the modeling approaches on how to model a dynamic system, there might be different modeling approaches, be it the first principles modeling or a data driven modeling. Now, before I proceed further, I would actually just to have some more interactions. I would like to ask the audience here, what do you understand by the first principles of the data driven modeling? Anyone would like to answer this question, you can please unmute yourself and please answer the question. So my question is, what is the first principles in the data-driven modeling? Anyone would like to respond? I think it would be good if so that it looks a bit more interactive.
Excuse me, ma'am. This can be an data collected from real-time experiments, and through that we can able to develop an algebraic equation that describes the behavior of a system.
Right. And that's which modeling, ma'am? Which one did you talk about? The data-driven modeling, right?
Data-driven modeling.
Right. That's right answer. So anyone else also wants to talk about the first principle modeling done? Okay, maybe I can frame put it in this way. So, ma'am, if you can only answer, so which, if you are working on any of these applications, which particular process are you following? Are you following the first principles modeling, or you are following the data-driven, or you're following both?
Yeah, we are using data-driven modeling.
And how are you doing, ma'am? If you can answer that.
Real-time experiments we are conducting, and we have identified parameters to be controlled. And, for those parameters, the real-time experiments data can be collected, and with that data, uh, we can able to develop a model so that from that model we can understand how the experiment, that is how the system is working.
That's great to know, ma'am. So, ma'am, which particular application are you working on?
Yeah, this is not my current research. Just for 4 or 5 years before, I have attempted to do. Just this is a mechanical based one, that is a flow stress prediction, how the stress behavior will be there and how it
Okay,
is moving with respect to time. So what are all the parameters it can we can able to control, like that soft computing techniques can be incorporated to predict the performance of the system.
okay, that's great to know, ma'am. Thank you so much. Anyone else who also would like to share their research and how they are doing or what particular modeling approach they're using?
Hello, ma'am. I'm Shiva. Can I talk now, ma'am?
Yes, please, sir.
Ma'am, I am working in that first principle modeling, ma'am. I have collected the data from a website, and there I am working on equivalent circuit model, ma'am, which is nothing but enhanced self-correcting model.
Okay, that's great. And so, which application area are you working on?
For electric vehicle in MATLAB, I'm working, ma'am. That is for battery modeling. I'm working, ma'am.
Okay. Okay. Thank you so much,
And
sir.
for okay, ma'am. Okay, ma'am.
Yeah, please, sir. Please, go on. Go on, please, sir.
Ma'am, for data-driven modeling, I have started, ma'am. I have not worked, but I am planning. I have seen few videos on that was system identification for data-driven modeling and neural networks. Ma'am. I have not worked, but I have gone through some works in that area, ma'am, for
Okay.
data-driven modeling.
That's for battery, right? That's what you're saying?
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am.
Sure, sir. We do have some existing examples available for data-driven modeling for batteries as well. We would request you to please get in touch with us after the session as well. We can share some resources. Ramana, who is in the call, has done a lot of work on modeling batteries and estimating the parameters using the data-driven approach. So please feel free to get in touch with us.
Okay,
Yeah.
ma'am. Okay, ma'am. Thank you, ma'am.
Sure. Thank you so much. So I'll continue. Thanks for the responses. So as mentioned by sir and from ma'am as well, so we have different modeling approaches, the first principles and the data driven modeling. The first principles where you know the dynamics of that particular system, and if you know the equations behind it, by using the approaches like programming, the block diagram, the modeling approach, you can basically model the dynamics of that system. And that's where the first principle modeling comes into picture. If you are working on the real experiments, if you are capturing the data from the hardware, and what you have is the response, the input and output response of your system captured from the hardware experiments, and if you use that to model and simulate your system in a software environment, that's where the data driven modeling approach comes into picture. As sir mentioned, the terms like system identification and neural networks, so these methods are used for identifying the parameters of your particular transfer function of your system, or the transfer function of your model, or basically all the parameters of your plant model or the controller as well, right? So this is where the data driven modeling comes into picture. And another thing is the parameter tuning. So if we talk about a hybrid approach, where you start with the first principles approach, but in order to make your simulation behavior exactly like your actual hardware experiments, that's where you try to tune the parameters, and that's how it comes in between your first principles and the data driven modeling, right? So once you have modeled the dynamics of your system, you basically make use of the parameter tuning approach to tune the parameters to behave so that your entire closed loop simulation behaves like your actual system on the hardware, right? So these are a few approaches which I use, and we'll see in the coming presentation how you can do it. So these are different tools which are used, being MATLAB, Simulink. If you're working on physical networks also, that's where Simscape comes into picture. We'll be talking about that. And if the data-driven modeling, which is a different chapter in itself, so we have other tools which are also available for this particular approach, right? So let's start with the very basic one, Simulink. Considering that you all might have used Simulink, sir, can you please let me know the background of the participants? They all might have used Simulink already, right?
I think everybody would have used, ma'am, but we have a mixture of departments, ma'am. A few are from mechanical, a few are from electrical. So you can go on, ma'am. You can give a short introduction. You can go on.
Sure. Okay. So I'll give a brief introduction to this as well. If you're talking about modeling a DC motor in Simulink, so it's not just the DC motor, be it any plant where even if it's a mechanical plant, if you talk about the mass spring damper system, you will always be knowing the dynamics of that system in case if you're following the first principles modeling approach. In the case of DC motor, if we try to solve the schematic by applying the KVL, KCL, or the basically the equation, if you apply the laws there, we'll ultimately get the equations for the current and the angular velocity, which is nothing but a differential equation, right? And in this case, which is a DC motor, these parameters are, for example, our DC motor is a electromechanical system, so it has the electrical as well as the mechanical components. In this case, if we talk about the equation for the current, then our equation is a differential equation having the parameters like inductor, the resistor, capital V being your voltage being fed to your motor, and capital K is your electromechanical conversion factor, omega being your angular velocity, right? Similarly, if we talk about the mechanical side of the DC motor, then that particular differential equation would have the components like the moment of inertia, this case again the electromechanical conversion, then capital T being your external torque, if you're trying to apply external torque to your motor, which will impact the speed of that motor, and small b being your damping coefficient, right? So these are the parameters which make up your differential equation in case of DC motor. And if we have to model this in Simulink, so as we said, Simulink is it has a graphical environment, It has built-in library blocks with which you can model and simulate your dynamic equations. Now, in this case, if you see, this is basically a differential equation, and we have used the mathematics library from Simulink to model this particular equation, right? To show this into action, I will actually open up the Simulink model. So Anand, if you can please let me know, are you able to see the Simulink screen?
Yes, I can see the screen, the Simulink window.
Yeah, thank you so much, Anand. So this is how, for the ones who are new to Simulink, this is how your Simulink window looks like. This is nothing but a text. We have written the entire equation here. And that's where your, the block diagram approach comes into picture. And in your Simulink library, you have all the built-in blocks depending upon your application. If we talk about the basic Simulink library, if it's a maths operation, because in this case we have the differential equations, so we can make use of this mathematical operations library to build that system. Similarly, if we are talking about different inputs, because it's a dynamic simulation environment, you may want to, change the input and see what's the impact of that change of the input on the output. So please make sure this is where we are talking about an open loop system, in this case, which is a DC motor, right? Similarly, if we talk about so this was the sink where we are trying to visualize the results, the sources where we want to have the different types of inputs. And not just this, you can even feed the input, which is from a captured data, if it is from outside the MATLAB Simulink environment, right? Similarly, if you are working on different applications, there are different toolboxes which are available and you can go and use them. So I'll start with the basic one. We'll see how this simulation works. So what we are trying to do is we have an input voltage of 12 volts and a zero torque. And we'll see what's the impact of, what's the impact of putting in a 12-volt input voltage onto the speed, right? So this is where we run the simulation in your Simulink environment. Just give me a second. So while the simulation is running, this is a plant model, right? We'll go inside this later on and I'll show you how it is built. But let's just quickly firstly see how the output looks like in this case. So what you see as a result here is that you have a 12 volts of DC voltage being fed into your system. Your torque is 0 because we didn't apply an external torque, and the speed of your motor increases, right? Now let's see what's the impact of putting in a step input voltage if it is changing from one level to another. And also at some point we also want to apply some torque to see what's the impact of applying that torque to that motor. And now if we run the simulation again, note this simulation is running for just 10 seconds because we have mentioned in our main Simulink window the simulation time as 10 seconds. You can even infinite, or you can change simulation time according to your application as well. So as a result of this simulation, you will observe that initially when the voltage was at 0 level, it's taking some time to update it, but let me just clarify. So when it's the voltage level is 0, the motor is not rotating, and when there is a step voltage of 12 volts, that's where the motor starts to rotate. And when you apply the external torque, that's where the speed will reduce, right? This is because of the result of the equation that you have built or modeled inside this model. So what we see here is this is basically a subsystem, and if we go inside the subsystem, we'll have our differential equations which are built. Please note, this is just for DC motor. If your plant model is different, if somebody is working on a mechanical application for a mass spring damper system, you will have your own equations, and that's how you can build it. So to build this particular equation, we have used the mathematical blocks to model the entire differential equation. I'll pause here for a minute for you to observe what's happening in this particular model. Just to clarify, so if we see this particular part, if I come to this section, what's happening is in my first equation, which is that's where I'm trying to solve for the current. That's V minus of IR minus of KW. So this particular adder block is being fed with a positive voltage and negative value of the current being multiplied with R, which is minus of IR and also minus of KW, right? So this particular signal which is coming out of this adder block is, as a result of our equation, is being multiplied with 1 by L, which is the inductor value. And further, it's being integrated here. So this is the result of our first equation. Similarly, the result of our second equation, which is for calculating the angular velocity, that's how it's modeled in this side. So this is how we are trying to model a DC motor plant model by using the mathematical, that's the first principles modeling approach using Simulink. Please note these values, capital R, B, K, these are just constants where we are these are the parameters of our system, right? So we are putting in the values of these constants. These are just variables. You can give the values to these variables back in your MATLAB workspace. Or you can directly put in the value of the gain in the block diagram itself. Is there any question so far on this particular part? Okay, so should I move it? Anand, is there any question which I need to address?
Hello, ma'am.
Yes, sir.
Ma'am, one participant has asked question regarding hybrid system, ma'am. Is it okay to ask now, or shall we proceed in the last, ma'am?
So you can ask now. If it is going to be addressed later on, I'll park the question for the later time. But you can please ask the question.
One participant, Srija Nair, has asked that, ma'am, can you give more explanation about hybrid system along with the batteries?
Yeah, so we'll be covering that part also. We'll be showing a model for hybrid system as well.
Okay. Okay, ma'am, then that is the only question from participants.
Okay. Thank you, sir. So I'll proceed to the next part. This is where we were showing how to model using the mathematical approach with Simulink. So moving ahead, this is the part of modeling a DC motor using the first principles approach with Simulink, right? Now we move to the next part. If we talk about another modeling approach, which is again a first principles modeling approach, and that's where Simscape comes into picture, right? For the ones who are new to Simulink as well, so Simulink is basically a mathematical modeling platform, but when it comes to Simscape, it's more of a physical modeling environment. And in this case, what you have is basically if you want to model a DC motor, again, if you don't know the dynamics of the basic system, if you don't know the equations behind it, that's where you make use of Simscape. And what you have is a schematic with you. And also, if you're having a more complex system or a circuit like power converters, where you don't want to, which also includes the switching elements, and you don't want to model the dynamics for it and follow the physical modeling approach, that's where Simscape comes into picture, which has more of the physical components, right? And you can again simulate the similar behavior. So this is how the physical network of a motor will look like. If you observe in this case, these blocks are all physical components. And for example, the resistor and inductor in this case are the actual physical components, and the connections also between the voltage source and the resistor in the entire circuit is where the actual energy is flowing. So that's the current which is flowing in this case, right? Similarly, if you see there's a difference in color on the other side, which is green. So this is for your mechanical systems. Um, so there, what happens with SimScape is, so SimScape basically is a multi-domain physical modeling tool. So it it has different domains like electrical, mechanical, thermal, if you want to make fluid systems as well, so it has libraries for that also. So in this case, what is being shown is that you can, integrate these multiple domains together on a single platform. For example, if you observe in this case, we're integrating your electrical along with the mechanical domain, right? Also, this is for a plant model. But if your controller model has been built in Simulink, so this also gives you provision to integrate your Simulink models with SimScape. So SimScape is a tool which is built on top of Simulink, and it has a connection available. You can directly connect your Simulink. You can connect your, not directly, but you can connect your Simulink blocks with SimScape. So that's where these conversion blocks are also there. These are needed if you need to connect your Simulink models with SimScape. So what this particular thing gives you is you can have a single platform approach to make your entire closed loop model. This is a plant model. In the next step, we'll go ahead and see how we can also add a controller to it, right? So this is the example of a DC motor. Similarly, if there is someone who is working on batteries and you have the RC equivalent circuits, you can make use of SimScape Electrical, and we do have existing examples available to inbuilt examples where you can use those examples and build on your application on top of it, in which SimScape Electrical has been used to model the RC equivalent circuits to make the entire series parallel combination of the batteries as well, right? And in that case also, if we talk about a battery, since we're talking about motor here, which is electromechanical system, if we talk about batteries, that's more of an electrothermal system. So because the thermal effects are also involved. So in that case, you also include the SimScape's thermal library to make your entire battery model, right? Similarly, we'll come to the power converters as well, which is like an entirely electrical circuit. So from the audience, I would like to, before I proceed further, have you used SimScape before? Is anyone who is working already on SimScape?
Yes, ma'am. I am working, ma'am. In the SimScape, I have worked, ma'am. Regarding battery modeling, we have worked, ma'am.
Okay, that's great. So you're using SimScape Electrical?
Hello?
So sir, yeah, sir, have you used SimScape Electrical?
Yes, ma'am. I have worked with the equivalent circuit model. I have worked, ma'am.
Okay.
Okay.
And you have also used Simulink for controls part, or is it just the plant modeling?
No, ma'am. I have used only for that mathematical modeling, that parameter optimization. I have worked. Little bit I have worked, ma'am.
Okay, and have you not worked on the physical? If you have worked on the mathematical model, so are you also making a physical model for your batteries?
No, ma'am. No, ma'am. I'm not.
Oh.
I'm not doing that, ma'am.
Okay.
Just I have learnt that 1 or 2 or 3 circuits which is available in the examples part. I have worked, ma'am.
Okay. Sure, sir.
Okay.
So if you plan to work on it, as I mentioned before, please let us know. We can share more examples which are coming up on batteries for first principles as well as the data-driven modeling.
Okay, ma'am. Okay. Thank you, ma'am.
So this is basically the physical modeling approach. how it differentiates with the mathematical, and where to use when. I would actually like to pose this question. If anyone can answer the basic difference between the mathematical and physical modeling approach, and if you can also let us know why do you prefer one approach over the another. Can please someone answer this question before we move to the converters part? Is there a preference for a mathematical modeling over physical modeling, or physical modeling over mathematical modeling?
Ma'am, Shija here.
Yes, please, ma'am.
Mathematical modeling is more preferred. Yeah, mathematical modeling is more preferred over physical modeling because the calculation becomes very easy and accurate. Whereas coming to physical modeling, at times it becomes like very difficult to debug the errors. I mean, whatever errors are there, to fix those errors and the cost and all is quite challenging. So I think a mathematical model is more preferred.
Ma'am, which particular application area are you working on?
Ma'am, I'm working on hybrid energy storage system for electric vehicles.
Okay, sure. Thanks for the response, ma'am. Anyone else also would like to respond to this before we? Yeah.
Uh, Ma'am, I'm Shiva, ma'am.
Yes, sir.
Hello. Ma'am, I think this the Simscape modeling is, I think, easy, ma'am, physical modeling, because we need not learn more equations. If you know just what are the physical elements available, I think it is easy for us to use. And also it has an option of converting that to a Simlink option, PS to Simlink option is there. So I think if you are knowing just the blocks, I think it is easy to work in Simscape, ma'am.
Okay. Thank you for the response, sir. So I would like to address how we think in terms of mathematical and physical modeling approach. Although everyone has their own area of application and they would have their own preference of the modeling approach as well. But if we think in this term, if you're talking about a simple linear system, and for example, if it's a DC motor, and if it's just a single motor, you would definitely prefer maybe the mathematical modeling approach, because it's easy to model the dynamics of a single motor. But when it comes to a non-linear system like the converters, which has switches involved, or if it comes to a system where you have multiple where you have a complex model where there are multiple motors involved, or if you talk about a system where there are different domains, for example, if it is a battery, you have the electrical and thermal domain also involved with it. That's where you would basically, you might prefer the physical modeling approach, because as sir also mentioned, since Simscape has the physical components, you don't need to get into the dynamics or the equation side of it. All you need to do is make your electrical circuit, or basically electromechanical or electrothermal circuit, right? So it entirely depends upon your area of application, which modeling approach that you would prefer. And it also at times depends upon the fidelity of your model. If you're talking about a linear model and you don't want to get into the dynamic behavior or the switching behavior, you might prefer just Simulink. But if you're talking about a higher fidelity model, or if you're talking about the switching characteristics as well, which are to be involved, that's where your preference for the modeling approach will change. So it's not, there's no hard and fast rule defined on which modeling approach works well for someone. So it all depends upon your application and your experience, or basically the time also that you have to build that certain application. As sir also mentioned, you can, in case of Simscape, you have all these physical components involved, right? And also to clarify, these converters, these converters are not actually for conversion from Simscape to Simulink. I want to clarify this thing. So these blocks are just to be able to connect the Simulink platform with Simscape. Because otherwise, what happens is if you try to connect your Simscape blocks with Simulink, they won't connect directly, because these are two different platforms. I mean, these are same platform, but they are built on top of each other. So Simulink is a mathematical platform. Simscape is a physical network, right? So to bring that connectivity, to make them compatible, that's where these blocks are needed. So you can connect the two of them, right? So these, just to clarify, these are not converting your Simscape to Simulink, but basically these are connecting your Simulink or Simscape to each other, right? Uh, so I hope this part is clear. I'll move ahead for better clarity. Let's talk about a closed loop model, right? If you're talking about again this plant model, the DC motor, that's where we had the DC motor as a plant model. And if you want to, include, if you want to do a closed loop simulation, and if you want to include a controller in this, we are using for now we are using this PID controller, and we'll do the closed loop simulation. Once the simulation works fine, you can generate the code and deploy to the hardware, right? Now, to demonstrate that, this is the model that we have. Now, what you might have is this particular motor model can be your Simscape model as well. And you can connect that using the converter blocks to your Simulink model as well, right? Now, in this case, what we are doing is we have a controller. What I'll do is I'll just delete this block. I'll bring in a new block.
Hello, good afternoon, ma'am.
Yes, sir.
Can I ask one question? Madam, I am from mechanical background. Actually, I want to complete my PhD in combustion technology, IC engine. So,
Okay.
madam, as far this Simulink is concerned, for any person to get for designing of the motor, so how Simulink will help in designing, how to understand the physics of motor, that which when you are doing any changes in design, so there are some physical aspect, mathematical calculations are there while you are considering this particular design. So how Simulink is helping really to design the motors, for designing of motor, if you have to do any change in the motor specification or something, how Simulink will help?
Right. Thank you for that question, sir. So I've brought in the model again. I'll come back to the controller part. So I've brought in the model for the plant model, which is the DC motor again, right? So you mean your question is, if I understand well, how you are able to use Simulink to design your motor, basically how you are able to identify the parameters of that particular motor also, right?
Yes, yes.
So what we are doing with Simulink is, as we mentioned, Simulink is a platform in which you can basically design with simulations. So as you know, in this particular example, I simulated the model and I could see the result. And in this case, since I was using my existing DC motors parameters data sheet, and I was putting in the values directly, right? And I was able to simulate the behavior and see the result, how angular speed is changing according to my different output, different input voltages. And if I want to see what's the impact of changing the parameter, what I will do is I will go ahead, change the value of this particular resistance, or change the value of inductance or any other parameter, and see what's the impact of that change on your output simulation. Now that is something which we are manually doing. Now, this is the first because this is the first principles approach, and changing the parameters will also, I'll show you this in the power converters part as well, how you can change the parameters of your system and see the impact on the output. This is a manual approach. But if you are considering approach where you want to automatically do it, so there is one more approach, as ma'am initially mentioned, the data-driven modeling approach, where, for example, if I have an actual DC motor, or say any other motor also, what I do is I run that motor, I give it some input, and I capture the response. So what I have with me is the input-output data. And what I need to do is I want to make a model for that. By making a model, I actually mean I want to identify the parameters of that particular model, right? Because I know the input and output, but in the simulation environment, only the parameters will actually help me to make that entire motor as a model. So what we do have in that case is we have a data-driven modeling approach where that's what the parameter estimation, that's where parameter estimation comes into picture. We give the input and the output response. We run the estimation. At the back end of it, it runs the optimization techniques. Simulink will run the optimization techniques. And as a result of it, it will give you the result for all these parameters. What is R, what is L, what is J, B. So it will give you the value of these parameters corresponding to your simulation result from the hardware that you have captured.
Okay.
So does it make sense?
And ma'am, basically when you follow the modeling approach, generally first we do the validation. So can Simulink can be also used for validation? Because I am not aware of this, because this is I have never used Simulink. So I am asking some basic questions to you.
Yeah.
Whether it can be used for validation purpose also, the Simulink, the model.
So validation again is a broad term. Can you please mention what type of validation? Are you looking for the parameters
Yes,
or
yes.
the
Initially, suppose, ma'am, when we go for any study for any simulation model, first overall we see that whatever model we are implementing, that the output is validating with standard literature or the earlier works. So can Simulink be used to validate the earlier works before proceeding for our current whatever the problem we have defined? So
yes?
that way we can validate.
Yes, sir, definitely you can do it. That's where if you have the earlier results in the form of data, you can
Okay.
directly feed in that data and validate your results. Even with our manual and automatic estimation results, that's where, if you remember, I mentioned in the modeling approaches, there's something called as parameter tuning. So that parameter tuning also helps you to validate your parameters. So
Okay.
whether your result or your simulations are according to your data sheet or not, or basically your previous research results or not. So that validation, if you need, so that is something which you can definitely do with Simulink.
Okay. Okay. Thank you, ma'am. Thank you for your explanation.
Yeah. So coming back to the controller part also, what I had done was I was connecting a controller with the motor. Now what we are doing is we are trying to see, okay, what is there in this model is we have a desired speed. We want our motor to rotate at a particular speed, right? And we have the actual speed also coming up. So what we are doing is we are comparing the desired speed with the actual speed, and the difference of that, which is an error signal, is being fed into a PID controller. Now you know that PID controller is something which gives out the controlled output, in this case which is a controlled voltage, and that is being fed to your motor, which will help us to match your basically desired result with the actual results. So what's happening in this case, if you see, is our the yellow line shows the desired speed and the blue shows the measured speed. But what you see is these are not matching at this time. And why this is happening is because our controller is not tuned, right? That's where the PID controller comes into picture, so that you can tune the controller parameters and your results can match. Now, again, in this case, there are two approaches. Either you manually go and change the value of your PID gains. That's where you put in the values of the PIDs. As sir also was asking, if you have your previous research results, you can put in those values and see what's the impact of that particular change. And if you're new to it, you can, for example, if you're not aware of the impact of changing the PID parameters, this is something which you can even use for teaching the students how the PID parameters make an impact, right? So what you do is you can click on the tune button. So what tune button will enable you to do is it will automatically tune your controller gains, that is the PID controller gains, according to your plant model, right? So when I click on the tune button, it will open up a PID tuner app. Another capability for the ones who are new to Simulink, Simulink and MATLAB has multiple apps which helps you to interactively, play around with the controls in that particular app. For example, this is for a PID tuner. You can interactively play with the parameters and then update it automatically, or basically generate the code out of it automatically. You don't need to manually write the code. You don't need to manually change the values as well. So this thing is, we don't recommend as such for students for who are undergraduates. We don't want them to actually go into the automatic mode directly, but it definitely makes a result if you want to validate your results. That's where the validation again comes into picture. If you have done the manual thing already and if you want to validate the results, that's where the auto tuning can also be useful. So if you see, in this case, we are getting the responses. The dashed response shows the block response. Block response means in our PID block, there were PI values were 1, 1, right? So this dashed response is corresponding to these PID values. But the tuned response is something which comes out automatically. So if I click on show parameters, you will see these are your PID's block response, block parameters, and these are automatically tuned parameters. Now, these automatically tuned parameters have come up as a result of a step response because we are giving a step plot. So what happens when you give a step input to your plant model? And if you want to, automatically tune the controller gain. So this is with respect to one particular operating point. So we have gotten these values of the PID gains. And you also see the performance and robustness parameters. Your rise time, which earlier was 22 seconds, now it has gone down to 0.4 seconds. Settling time is 1.62. So what you can even do is, as we mentioned, you can interactively play with these controllers. So you see there is a slider on top. If you want to make your system respond faster, right? That's where the rise time has reduced, and you can while you are changing these parameters, you will see your response parameters, the performance parameters will change. Now that depends upon what you want as your system, right? It will change from application to application. Once you have your desired results, you can simply click on the update block, and when I come back, if I close this particular app, I will come back. So you will see my parameters are automatically updated. The controller gains are updated. And if I click OK and run the simulation now, so now you see the results are better because our PID controller gains have been, tuned. Although we did it automatically, so the controller gains are tuned, and your desired speed, your measured speed, is matching with your desired speed. That this is an example for a simple DC motor. Similarly, you can now, this is a linear system. You can even have non-linear systems, which we'll be talking briefly in the next one as well for the converters. So if somebody is working on converters, that is again a complex non-linear system. For that also, you can do the automatic controller estimation. Any question on this part so far? Is there someone who has used the auto PID tuning capabilities from Simulink, those who are the users of Simulink or MATLAB? Anyone would like to respond?
Ma'am, you can continue, ma'am.
Okay, sure. Thank you, sir.
Mm.
So this is the part where we talked about the closed loop model for a motor itself. Now let's quickly come back to the presentation again. We spent some time on this part because there are users who are new to MATLAB and Simulink as well. And we took an example of electromechanical system, because DC motor is something which is used for, and PID controller definitely is used by both mechanical and electrical domain, definitely. Similarly, this is an example of a battery model. As someone also mentioned, we talked about the RC equivalent circuit models. So we do have all these examples available. And if you see these results here, these results are basically the simulation results, which are done for the prior research that you might be having, and you can compare those results as well, and you can simulate the behavior of your batteries at different parameters or different changed inputs. In this case, this is being simulated at different temperatures, right, at different times. So all these simulations are possible. Similarly, you can model the batteries. I am not getting into the depth of batteries, but if somebody is interested, please feel free to reach out to us. We do have separate content available on batteries, but the approach will remain the same. So you can even model your batteries from the data sheet. If you have the data sheet parameters, so you can model it as a particular component, or if you want to, if you want to do the component level modeling, where you have the different RC equivalent circuits along with the thermal models involved with it. So that also you can do. So it depends upon what type of it again comes to your approach, whether you want to follow which particular modeling approach. Similarly, if you have modeled your battery, then you would also, if you're looking into designing a controller for that, which is your battery management system, and then generating the code for that and deploying it to the hardware to do the closed loop simulation for batteries as well. Now I'll quickly jump into the converters part. In the interest of time, we have like half an hour or so left. So I'll continue with this since we have talked enough about SimScape for motors and all. So I won't spend much time on this. It's a similar approach. And then I'll jump to the hybrid electric vehicle, the full vehicle modeling part as well. So if you see, these are for the converters. If somebody is working on nonlinear power converters, this is for the case of DC to DC power converter, right? And you also may need to design the controller for these. So what we are showing here as a result demonstration is as an end result. We have used the Texas Instruments DC-DC LED developer kit. Now this has a SEPIC converter infused in it, right? And we are trying to control the switching behavior of these LEDs. We're trying to switch on and off a specific LED, or we are trying to manually control the brightness of these LEDs. This model, we try to build it with Simulink and SimScape. Right. So what is done, if you talk about
ma'am, one
yes,
small
please,
doubt. Yeah, ma'am, actually two doubts I have. Number one, closed loop system over open loop system is because to eliminate the errors, right? We eliminate the errors when we use the closed loop system, no? And second doubt I have is why PID controller, why not PI or PD controller, ma'am? I'm not from control system background, so this is the if you can clear this doubt, why PID controller? Then it would be good.
Ma'am, in this case, we have used the PID controller, but that depends on your application. For example, in the case of converters, it's just the PI controller. That all depends upon how your parameters are impacting the performance. So it will entirely again depend upon your application, which controller you would like to use. It's not always the PID controllers. You may also be working on some other controllers as well. But I think that will depend upon your application. That's the thing which I can answer at this time. I'm not sure about the first question you mentioned. Were you trying to say that simulation, with the simulation, you're trying to reduce the errors?
No, ma'am. I was trying to say that we can use open loop system also, no? So we are going for closed loop system. Is it to reduce the error, or can there be any more elaboration also? Like why closed loop system? Is it always
Okay.
like desired output should be equal to like?
Yeah.
That's
So
the only reason. That's a question I have.
yeah, so that's the only thing. So that is just again, if you're working on a open loop system, The open loop system would not involve your controller in that, and you can simply do the plant modeling. That's also there. Again, that depends upon your application. But if you want your particular plant to behave in a certain manner, that's where the controller would come into picture, and because that will make an impact on your required behavior, or how do you want your plant model to behave. So that's why we talked about the controller. But if you are working only on the optimization of your plant models parameters, you might not be working on the controller. So your application doesn't always need a controller.
Okay, ma'am. Thank you.
Right. So coming back to this, the converters part, again, we'll have a similar workflow. We'll talk about the plant model. Again, as ma'am mentioned, there are different things, different features which are involved in a plant model itself. In this case, we'll try to see what's the impact of changing a particular parameter and see the result on the output. Again, in converters, since there are switching behaviors or the thermal behaviors involved, then how to deal with that, how we can determine that. If you're working on a controller, also how we can design a controller for your specific plant, and then implementation, right? So I'll start with the first part where we talk about SEPIC converter. So that's where we have used DC SEPIC converter as an example. If you see, this is an entirely electrical circuit, and what we have used is SimScape Electrical for this, which has all the physical parameters, which physical components like your inductor, capacitor, the voltage source, your voltage sensor to calculate the voltage, the current sensor to see the current flowing in the series, and the connections which are there are electrical connections, right? So this we have discussed already. And as the converters, they do have the switches involved. So we are starting by an ideal switch, and it's being fed with a 0.6 duty cycle for the switching. Now, as Sir asked initially, how are you able to model it with Simulink or Simscape, right? In this case, you will see if we have a converter, since Sir was from mechanical background, you might have a different application, but you can relate to this one. So in this case, we know the converter, if it is working in a continuous conduction mode, we know the parameters from the data sheet. In this case, we are aware of the data sheet parameters. So we have put in the values, and we have modeled this with Simscape Electrical, and the values also we have added, right? In this case, I'll skip this video. So I'll come to this part. We have put in the values of the inductor, the capacitor, and given a 12 volts of DC voltage and a 0.5 duty cycle. So if you're not aware of it, you will play with the values and see what's the result of that thing onto your simulation. In this case, the behavior of the converter is supposed to be 12 volts output itself. So that's why, because we are using it in a continuous conduction mode, our output comes out to be 12 volts. That depends upon the equation. So what we have as a result in this case is we have an output voltage becomes equal to D upon 1 minus D of the input voltage. That's what the formula for the output voltage is. And if we solve that, the output comes out to be 12 volts itself, right? Now, as coming back to Sir's question, what's the impact of changing the parameter? So if you see, what we have done is, if you see these knobs, so the ones who are new to it, these just come from a dashboard library in Simulink. So we don't need to get into that for now. You can even manually change the parameters by clicking onto a particular component. So in this case, this particular knob is connected virtually to your inductor, and this knob is connected virtually to your capacitor, right? And you will see, if we change the parameters of your system, for example, we're changing the resistance, load resistance, or if you're changing that inductance value, and if we change and if you run the simulation, your output is no more 12 volts, right? That's how you see the impact of changing a parameter. Again, if you open up the current sensor result, the ones who are from the power electronics background, they will know that now it enters into a discontinuous conduction mode. So these simulations, the idea to show, because the audience here might be from different backgrounds, so the idea is to show how you can, select a specific parameter depending upon your simulation results. So you simulate your model, you see the result, according to that you can change the parameter, right? That's how MATLAB Simulink and Simscape helps you to model a specific system, be it your plant model or a closed loop model as well, right? Now, again, this is specifically for the ones who are working on converters. It might not be relevant for everyone because this is a highly electrical thing. So what we have done in this case is, if you are trying to add a non-linear component. So earlier we have been talking about the linear components only. So if we add a non-linear component to it, in this case, we have added a non-linear switch, which is an N-channel MOSFET switch. Now, again, coming back to Sir's question earlier, if you have datasheet parameters. So if you observe this particular switch in your application, you might have a different component. And this particular switch has all the parameters which are present in the datasheet of this component. So what you can do is drag and drop this block from the library, put in the value from the datasheet, and simulate your particular component in a circuit, right? Once your simulation works fine and you are able to match your results with the datasheet results, you can put into your actual entire circuit. So what is being done in this case is, we use the N-channel MOSFET switch. Unlike the linear switch, this is a non-linear switch, semiconductor switch, and you can put in all the dynamic, ohmic resistance and the static parameters from the datasheet and simulate the component and compare the results with the datasheet results. You can validate the results also. Then put it in your actual circuit. To bring to the notice, this particular circuit also talks about the thermal component. So you can right click on it and enable the thermal port. When you enable the thermal port, you can make use of Simscape's thermal library, which is like orangish in color. Every library will have a different color for the differentiation. So you can even model your thermal behavior. Now this also holds good for the ones who are working on battery models. So they can connect their RC equivalent circuits with the equivalent, thermal models as well. Right? So this is how you can, model and simulate the thermal behavior also. Now, coming back to the third part, which is control algorithm, I would actually skip this part for now. If there is someone who is working specifically on a non-linear circuit like converters, you might face a challenge when you're coming to the controls part. When you are talking about a control model, which in this case is like this, so you have your plant model, you take the output, you compare it with a reference, and the control PWM is feeding into your switch, right? So what happens in this case would be, when you're trying to automatically tune the controllers, your system will linearize to a 0 level. The ones who have used it already, you might have come across this challenge many times because it's a non-linear model, right? So in that case, I'll just skip the slide, but I'll just verbally tell you what you can do is, there is a provision in Simulink itself to identify a linear transfer function for your non-linear plant, right? It has a few steps involved. What we'll do is, we'll share these presentation slides. It has the videos in it, and you can follow this video, and there are a few steps which are involved. So what you can do is, you can simply identify a linear transfer function for a non-linear plant. Once you have that will help you to basically identify the controller gains, and you can again follow the previous steps that we did already for the controller. But in this case, how it is different from the earlier one is, this is a non-linear plant model. The DC motor was a linear plant model. So that was a very straightforward process, right? So if you see in this case, there is a plant model. When you click on this part, you will see how you can identify a new transfer function for your plant itself. So I'll skip this part. If there's someone who is interested in this, please let us know. we can take it up separately, but just in interest of time, because there was a question around the hybrid models as well, I would definitely like to cover that as a priority. Right. So this is the part for the PID control. This is the same process which I showed earlier. So what we are seeing is once the PID controller parameters are tuned, we can see the simulation results. It tries to, your simulation actual results matches with your desired results. Now this is for the ones who are working on the closed loop simulation part as well. Right. So this is the fourth part is also very important if we talk about the code generation perspective. So what we have is, along with the MATLAB Simulink tools, there is something which is called as the hardware support packages. As I mentioned, MATLAB Simulink has the capabilities to automatically generate the code and deploy to the hardware. In some cases, like Texas Instrument, it has a direct integration available. So there are direct device driver blocks which are available, and you can simply download them. You don't need to separately purchase it. If you're using a licensed version of MATLAB, you will have the access to the add-on support packages as well. We had very good results of educational research scholars who have been making use of these hardware support packages for, automatically generating the code for their controllers and deploying it to the Texas Instrument hardware. So you see, you can generate the C++ code, or basically the VHDL code if you're working on FPGA targets, and do the implementation. So what this particular hardware support package, as I mentioned, what it gives you as a capability is, you will see these blocks in your Simulink library. Now these blocks are nothing but the device driver blocks. So what you can do is, if you see this entire system, your application layer and your software layer, which is your device driver, all this comes into one frame, and with just one click of a button, you can take your Simulink model to that particular Texas Instrument board, hardware board, by mentioning which particular output or EPWM, which controller you are using, and mentioning its configuration parameters. So as I mentioned, this is a specific hardware support package for TI. So this is a single support package for all its Texas Instruments controllers, and all the latest Texas Instrument controllers are supported with MATLAB. So when you install this, you will see these set of libraries which comes into your Simulink model. So once you have built your Simulink model, you can connect your model with these library blocks and get this as a result. So what is happening in this part is, I'm trying to manually control the brightness of the particular LED. I'm changing the value from my Simulink model. The results are coming on the Simulink, and it also comes on the hardware. So in this case, I manually turned off all the LEDs. I can switch on and off a specific LED as well. I can control the brightness by using these knobs. So whatever I'm doing is from the Simulink, and the results are being shown onto the hardware as well as your simulation tool. Right? So this is the auto code generation capability. You don't write even a single line of code. It is done automatically. Okay. So moving ahead, we did talk about different components, right? I briefly talked about the batteries. I showed you how there are Simulink models or capabilities available for motor modeling and control. Then we even quickly talked about the power converters. So these are the different components of the EV, right? One particular research scholar might be working on the motor modeling part, another person might be working on converters. But if you want to see what's the impact of your component on the entire vehicle simulation, these are some of the reference models which are available. So when I'll share these presentation slides, you will see this is a hyperlink itself. This is a downloadable model. You can simply download it. This model is built entirely on Simscape platform. This is to answer the question which was there on hybrid electric vehicle model. So this model is a hybrid electric vehicle model built on Simscape electrical, not just electrical, but Simscape as a platform. So when you will get inside this electrical model, you will see there are models for motor converters, there are models for drivers, and the batteries as well. There are different variants of the models which are available. If somebody is from the mechanical background, you might be interested in seeing the vehicle dynamics model. So for the ones who are from mechanical, Simscape, the way it has libraries for electrical, mechanical, thermal, there is a library available for the automotive applications. That's the Simscape drive line. So that is used in this particular block to model the dynamics of your electric vehicle. And this entire full model is for the full hybrid electric vehicle simulation. The good thing about this is you can use this as a reference, make your own model and replace that particular component in this model and see how the simulation for the full vehicle looks like. Right? Similarly, now as I mentioned, this is entirely based on Simscape. We have another tool called as the powertrain block set. Now, this is a full electric vehicle or hybrid electric vehicle simulation platform where you will have the reference applications. If you see, this one is for the EV reference application. There is one for the hybrid electric vehicle reference application also. So you will see the entire electric vehicle as a system. In this case also, if you have your own component, you can go inside this model, replace that block with your own application, with your own component, and then run the entire electric vehicle simulation. One thing to note how this is different from the previous one. This model has been built entirely on Simscape. This one, Powertrain Block Set, is a tool which is built on Simulink. So at the back end of it, it uses all the mathematical modeling approach, right? And the great thing about this particular tool also is that it has the entire equations which are used for the dynamics. It's open. Every block is open. You can go inside it and see how that particular equation has been modeled, and you can even modify on top of it. So it doesn't have any closed blocks. It's all open blocks, right? So what this particular toolbox gives you as a capability is you have good ready to use plant and controller models. It provides an open and documented models. You can open them and use them. It also has very fast running models, which you can use with the HIL systems. So if somebody is working on powertrain, please get in touch with us. We can share. You can also get started with this example areas. But if there's some challenge which comes up, please feel free to reach out to us. So there are the existing hybrid electric vehicle example, or basically the electric vehicle reference application, conventional vehicle reference application. So all these are available as ready to use examples. So these are the different libraries which are available in this particular block set. You can make use of, for example, in this case, it's making use of the propulsion library, and the entire engine model is basically being fed and used with other block sets to make the full electric vehicle model. Another good thing about this one is, even if you are having a Simscape model, so as you know, Simscape and Simulink can be connected. So you can go inside this particular one, although it's built on Simulink, but you can go inside it and replace the Simulink block with your Simscape block by using the proper conversion blocks along with it, and simulate the entire electric vehicle model. Right? So these are some of the examples which are there. So I think the time is up also. So we do have some call to actions. We have these reference ready to use material for you. There is a webinar. Somebody is working on specifically on converters. Here is a webinar for you. There are some white papers available for power conversions and for HIL as well. I have not added a reference for batteries, but if somebody is working on that, please get in touch with us. These are the full EV simulation examples. So you can simply use this, that particular model for electric vehicle simulation and for the powertrain block set as well. So this is it from my side. I'll probably go back to the Google Meet platform to see if there are any questions for me. Otherwise, by the time, if there are no questions, I would actually request you, I'll put this feedback form into the chat. I would request you all to please share. Thanks, Ramana. I see you're answering most of the questions. So I'm putting in this feedback form. We would request you to please give us the feedback, and also we have posed the question if you want us to get in touch with you for any help regarding the curriculum or the research. You can respond to that particular question and we'll get back to you for sure. Till that time, we still have like 2 to 3 minutes to go. Please let us know if there's any question. Thank you so much, Ramana, for answering the questions.
Hello.
Yes, sir.
Hello, madam. This is Yuvraj from NIT Pondicherry.
Yes, I can hear you.
Can you hear me, madam?
Yes, yes. Yeah, I can hear you.
First of all, thanks for your wonderful presentation, madam.
Thank you, sir.
Apart from electrical vehicle, I'm having few doubts, general questions related with the power system point of view in MATLAB.
Sorry, sir, I'm not able to hear you fine.
Apart from electrical vehicle relevant informations, I'm in need of few general details with relevant to power system point of view. Shall I ask the questions from those areas?
Yes, sir, you can definitely ask those questions now also, and if you want to separately get in touch with us, that is also fine with us. Anything which is convenient.
Okay, now itself I will ask, madam.
Sure,
Two questions
sir.
I'm having.
Yeah.
My first question is, I want to connect GPS module with MATLAB in order to achieve time stamping.
Okay.
That is my first doubt. How to connect the GPS module with MATLAB to obtain time stamping? That universal time coordinated UTC time is there, no? That timing I want to achieve by means of using GPL module connectivity along with MATLAB.
Okay. So that connectivity is possible, but that will depend on the application which you're working on and why would you need that part for EVs. That's something we can discuss as well, but GPS module connectivity with MATLAB is possible.
Okay, fine, madam. My second question relevant to power system protection point of view by means of using MATLAB.
Sorry, sir, I'm not able to hear you fine. Ramana, are you able to hear sir properly?
Yeah, I can hear him. Yeah, please go on, sir. What is the question?
That is, the question is, based on the data like resistance and reactance data, I want to plot RX diagram, especially in power system protection, that too in distance relay. How to plot the RX diagram by means of using the data, available data like resistance and reactance. Any assistance is there in MATLAB, with MATLAB?
Yeah, to answer your question, it is completely possible.
Okay, sir.
Now, I need some data from you. Now, if this is resistance and reactance, are these parameter values in a physical modeling environment like Simscape or using Simulink blocks, some constant or blocks?
By means of using Simulink block, after running that block, I got both resistance and reactance values. I just saved those data with workspace. After that, I want to plot the distance relay characteristics. That characteristics uh, shows different zone settings along with the different zone settings like zone 1, zone 2, zone 3. Especially this one is relevant to power system protection, the two relay point of view, distance relay point of view, sir.
Yeah, I understand. You have impedance relay, reactance relay, more relay, all those relays,
Yeah,
right? Now
absolutely,
you want
absolutely,
RX
absolutely,
diagrams
sir.
for that. You want RX diagrams for that. So once you have the simulation, did you try using plot command?
Yes, sir.
Yeah. So what was the challenge for you on that? You should be able to use it directly.
No, sir. Actually, after running that Simulink block, I got the values like resistance and reactance. What step I have to do proceed in what next? I'm
Okay.
actually don't know.
Can you share me the details on mail? I will assist you with that.
Sure, sir. Definitely.
Yeah, I'm posting my mail in the chat window. Please write to me. I will be able
Okay,
to
sir.
assist you.
Oh, fine, sir. Thank you so much.
Sure.
Okay.
Thank you, Ramana. So the issue with my system is I have some my downloading speed in internet is not that great. I'm not in India right now, so that's what the challenge is. But if there is any other question, also please you can reach out to us. I should actually. So Ramana has posted his email address. I will also do it. So if there are further questions, please do reach out to us.
Good afternoon, madam.
Yes, sir.
Madam, how hardware in the loop software is better to simulate electric vehicles?
So you mean how hardware in loop software is, or how hardware in loop can be done for EVs basically? That's what the question is?
Yes, madam.
Right. So, sir, in that case, what I understand, so we do have the solutions for HIL through SpeedGoat. So there are different platforms which are there. MathWorks works very closely with SpeedGoat. We do have reference examples available. The integration of MATLAB and Simulink with SpeedGoat. So what happens is for your plant models, you can actually generate the HDL code and deploy it to the FPGA targets which are used in the speed code setup. So what will happen is that particular HL system would behave like a virtual vehicle. So what you are able to see is you are able to simulate the behavior of your model, not in just simulation environment, not just in software environment, but also along with the hardware, which is not the actual hardware, but it is a prototype. So that's how the HIL simulation works.
Means to check the velocity profile of the vehicle, madam?
Yeah, so that also can be done along with the HIL system itself. So the examples that the reference that we have, it also enables you to check the velocity profile also.
Okay, madam.
You can use the standard life cycle for we have reference models. I also pasted some example, so you can go through that.
Sure, sir. Thank you.
Yeah.
Is there any other question? If you're asking the question, please feel free to post the questions. And meanwhile, we would request you to also fill in the feedback form. This will help us to get back to you if you are looking for further assistance from our side in terms of curriculum or research help. We have put in the feedback form in the. Yes, sir.
Madam, to have the better motor dynamics, Simscape is better, madam, for the MATLAB.
So for what application you mentioned for motor?
For motor means for switching angles, for altering the switching angles, or in having some design alterations in the motor. So for that case, Simscape is better, madam.
Yeah, we would actually say if it comes to if you want to study the dynamic behavior and if it's a complex model for a motor as well, we would recommend using SimScape for that. But it also depends upon how much the fidelity of your model is. But yes, if it comes to this complexity where you're talking about the switching behavior, also that's where a physical modeling approach is recommended over the mathematical modeling approach.
So for that, SimScape is good, madam.
Sorry, sir.
So for that, SimScape is good, no, madam.
Yes, so you can use SimScape. Also, there's another tool. If you might have been using it already for lower fidelity models, like we have Sim Power Systems. I think there might be multiple users of that already, but you can try out with SimScape Electrical. But depending upon the application, you can see if SimScape or Sim Power Systems suits more. Whichever, both of them are physical modeling approaches.
Madam, can we write programming by using Python or other software also in this SimScape, madam?
So, sir, SimScape basically is a tool. This is on top of Simulink. So, MATLAB is base. On top of it is Simulink, and SimScape is again a part of the MathWorks product family. SimScape tools are built on top of. So, the language is SimScape as a language. You cannot write Python code for SimScape, but if you already have, that's a different application, right? If you already have your Python codes for some other application, there is a possibility to integrate Python with MATLAB. But SimScape and Python